This is a problem to find the extrema of this piecewise function. So piecewise function, as you might remember, has multiple pieces, and we're given the function, and we're given the x values where that function applies. So the first question is, what is the domain of the function? So to find the domain of the function, really I need to find the domain of each of the two pieces. So let's go to the next page here so we can see it a little bit better. If I'm looking at my top piece right there, well, it's a polynomial. And I know that a polynomial has the domain negative infinity to infinity. There are no denominators, there are no radical signs with variables under them, there are no logarithms. It's a polynomial. Domain is all real numbers, except this is telling us that it goes x is less than 1, less than or equal to 1. So the domain of this piece is really negative infinity up to negative 1, inclusive. Now I'm looking at this piece, and it's also a polynomial. So again, the same thing. No denominators with variables, no radical signs with variables in the radicand that have an even index, no logarithms. So again, the domain of this piece here is negative infinity to infinity. So if I wanted to unite those two in the same function, it would be 1 to infinity. But what we have here really is a domain of negative infinity all the way to infinity. The 1 is included in the top piece. It's excluded in the bottom piece, but it doesn't really matter because it's just one piecewise function. So my domain of the function is negative infinity to infinity. Now I need to find the derivative of the function. So again, here's our function, and our function has two pieces. So it kind of stands to reason that our domain is going to, that our derivative is going to have two pieces. So the derivative of the top piece, I think I'll write it like this. I'll write f prime of x. Well, the derivative of my top piece is negative 2x minus 2. And that's for x less than or equal to 1. And my derivative of my bottom piece is negative 2x plus 6. And that's for x greater than 1. So finding the derivative of this piecewise function, not that hard, primarily because the pieces of the function themselves are not that hard to find the derivative of. They're just polynomials, and polynomials are pretty much straight up the power rule. But now I need to find, okay, so that's my derivative. I'll put it right there on my answer sheet. So the derivative of the function is right there. Now I need to find the domain of the derivative. So again, I'm going to find the domain of each piece. And so this is a linear function, and that's a linear function. And the domain of any linear function is, again, negative infinity to infinity. There are no x values that don't count. No denominators, no radical signs, no logarithms. The only question I have is at this point right here, where x equals 1. Because it's a piecewise function, I don't know what the, I don't know whether or not it's continuous, or if it's continuous, whether I'm actually going to have a derivative there. So I'm going to find out what is the value of the derivative. That is, what is the slope of the tangent line for each of these two pieces. So at x equals 1. So f prime of 1 coming as x approaches 1 from the negative side, that's this right here where x is less than negative 1. Well, I'm going to substitute 1 in, so I would get equals negative 2 times 1 minus 2. So that's negative 2 minus 2. It's negative 4. So that is the slope of my tangent line on this piece of the function. What is the slope of the tangent line on this piece of the function? So let's do this. Let's go. What is it? What is f prime of 1 as x approaches 1 from the positive side? That is, where x is greater than 1 and I'm getting closer to 1 from the positive side. Well, I would have negative 2 times 1 plus 6. Well, that's going to equal positive 4. So I have a different derivative from the left and the right as x approaches 1, which means the derivative at x equals 1 does not exist, because the derivative has to be the same from both sides in order to be able to say that there's a derivative. So my domain of the derivative here, part C, is negative infinity to 1, parentheses, union 1 comma infinity. The derivative does not exist at x equals 1, so that's a piece that's missing in our domain. So next, I have to find all the critical points and the endpoints, the x values. So a critical point of the function is where f prime, or the derivative, either equals 0 or does not exist. Well, I've already found one point where it does not exist, and that's where x equals 1. So I can go right back here, and I can say, well, I know I have one x value, x equals 1. It's critical because the derivative does not exist, but it is not stationary because the derivative is not 0. Stationary is where the derivative is 0. So that's one point that I can fill in. Now the next thing I need to do is take a look at my derivative and find out at what x values does it equal 0. Well, that's not too tough. My derivative is a piecewise function in itself. So I just look at both pieces. So I say negative 2x minus 2 equals 0. Negative 2x equals 2. X equals negative 1. So at one of my points, I know that x equals negative 1. I haven't found the y value there yet. That's going to be a critical point, so that is going to be critical. And it's going to be stationary because the derivative equals 0. And let's do the other side here, the other part of the piecewise function. Negative 2x plus 6. Where does that equal 0? Well, negative 2x equals negative 3. I'm sorry, negative 2x equals negative 6. Divide by negative 2, I get x equals positive 3. So that's the other place where I have a critical point. So that is at positive 3. It's critical and it's stationary. Now, are any of these going to be endpoints? Well, no, none of them are going to be endpoints because the domain of my function is negative infinity to infinity. I don't have any endpoints. My function is going to go to infinity positive and to infinity negative. It's never going to end. So I'm back here to my function, and my points are 1, negative 1, and 3. Those are my critical points. And I need to find the y values of those points. Well, what is f of 1? Well, I'm going to use this top part because the domain of the function says where x is less than or equal to 1, I use this function. So f of 1 is negative 1 squared minus 2 times negative 1 plus 4. And that is equal to -1 plus 2 plus 4. That is equal to 5. So at 1, the y value is 5. I'll write that in. At -1, so what is f of -1? Well, that would be -1 squared minus 2 . Okay, I just saw I made a mistake. Top part, -1 squared. This would be 2 times just 1, positive 1, plus 4. So I'm going to get -1 minus 2 plus 4, which equals 1. So at f of 1, f of 1, my y value is 1. Let's go back over here and fix that. F of 1, my y value is 1. Sorry, at least I caught it before the end. Okay, now f of -1, now it's 2 times -1 plus 4. And that is equal to -1 plus 2 plus 4. That is equal to 5, not that. So at -1, it's equal to 5. And then at 3, f of 3, that is equal to negative, because 3 is now greater than 1, so that's -3 squared plus 6 times -3 minus 4. So that is -9. I'm just messing up left and right here. It's not -3, it's positive 3. Plus 18 minus 4. That is equal to 5. So now, after my little arithmetic errors, I have the point 3, 5. I already determined that none of these are endpoints. And now I need to determine whether they're maximums, minimums, or neither. I'm going to put together a little graph and see if I can figure out what these points look like. So I have the point 1, 1. I have the point -1, 5. And I have the point 1, 2, 3, 5. Now, those are the only possible points where my graph can make any turns, because the only place a graph can change directions is at a critical point, and those are the only critical points that I have. So I know that I have to be going up from here and up from here. And I can't turn around anywhere in here or anywhere in there, because in order to turn around, I would need to have a critical point, and I don't have any other critical points. So I know that those are going to be going up. So the point 1, 1 at least is guaranteed to be a minimum. Now whether it's going to be an absolute minimum or not, maybe I'm not sure yet. Because it's possible that this graph can go like that, or it can go like that. I'm not exactly sure which way it's going to go. If it goes like that, then my point 1, 1 is only going to be a relative minimum. If it goes like that, in other words, just having like the graph of x cubed, you know, where it's going up, and then I get a stationary point, which is critical, but then it continues going up. If it looks like that, then it will not be an absolute, then it would be an absolute minimum. So first let's check and see which way the graph is going to go by testing a point. So this right here is the point 1, 1. And this is the point 3, 5. And this is the point -1, 5. So why don't I test the point, I don't know, x equals 4. Because at least that'll tell me in which direction this part of the graph is going to go. So if I test the point x equals 4, I'm going to use this part of the piecewise, because it's for x is greater than 1. So I would have -4 squared plus 6 times 4 minus 4. Well, that gives me -16 plus 24 minus 4. Well, -16 and -4 is -20. Plus 24, that means my y value at 4 is going to be 4. So it's telling me that this graph is going to go down. And that's the last turning point. It's just going to keep going down forever. Let's test a point on the other side. Let's test -2. So I want f of -2. Well, -2 is in this part of the piece. So it's going to be -2 squared minus 2 times -2 plus 4, which is equal to -4 plus 4 plus 4 again. So those are going to cancel out. And I find out, again, it's equal to a -2, it's equal to 4. So my graph, again, is turning, and it's going down. And it's going to go down forever because there are no more turning points. So I can see that my point -1, 5 is a maximum. And as the highest point on the graph, it is also an absolute maximum. And I can see my point 3, 5 is a maximum. And as the highest point on the graph, equivalent with that, that's also an absolute maximum. Now, just so you think about it a little bit more, if I'm looking back at my original function, this piece here as a quadratic is a parabola. I know it's a parabola because it's a quadratic, and it also has a negative leading coefficient, so it has to be a parabola going down, down. As does this one have to be a parabola going down, down. So I didn't really even need to test these points here. I knew that this function overall was going to be like that, and I knew that this function overall was going to be like that. And right here, I happen to have a cusp, because both of these functions meet right at that point 1, 1. Continuous, but and we showed it was continuous when we did this way back finding the domain, but there still isn't any derivative right here, even though it's continuous, because it's a cusp. Finally, I decided to graph it just to check my work, and it turns out exactly what I thought it would look like. So you can see in the Desmos that if you want to enter in a piecewise function, you enter in the function here, and then in brackets, you put the domain of that piece. So I put x less than or equal to 1, that's this nice red function. I put x greater than 1, that's this nice blue function. So if I remove those brackets, you can see the whole function here, and again, you see that it is an upside-down parabola, but now it's not a piecewise function because I wouldn't pass the vertical line test.